So, students, welcome back to this course on materials in mechanical design. So, in my last two videos, what we what we have seen is that we were able to predict the longitudinal modulus of the composite, which we say is EL, through this expression, which we say is EL is nothing but EF VF plus EM VM, where these all variables have their meanings, which we have already understood clearly. We have also seen that the gain in stiffness, that is the ratio of EL to EM, is depending upon two parameters. The first one, the stiffness ratio between the fiber and the matrix, that is EF upon EM, and the second one is the volume fraction of the fibers. Both of these things give us the ratio between EL to EM, that is the gain in stiffness in the matrix that you achieve by forming a composite material. The next topic which we pick up today is on load sharing between the fibers and the matrix. We have already said that we are actually taking the equal strain assumption, where we've said that because of the assumption that there is perfect bonding between the fiber and the matrix, we were able to say that all of them will elongate by the same amount, and that is why the strain in the composite will be equal to strain in the fiber equal to strain in the matrix. Simultaneously, we have said that so this is what we have said, that epsilon f is equal to epsilon m is equal to epsilon c. We have also said that the total load on the composite, if I write it as PC, is shared between fiber and the matrix, that is PC is equal to PF plus PM. We are interested to know that how much of the load is shared by the fibers and how much of the load is shared by the matrix, and that is why we'll move forward on these lines now. So when I write the equal strain assumption here, that is epsilon f is equal to epsilon m is equal to epsilon c, I can rewrite this expression using Hooke's law as sigma f upon EF equal to sigma m upon EM equal to sigma c upon EC, and this sigma c upon EC is again can be written as sigma L upon EL, that is the modulus of the composite in the longitudinal direction. So the sigma c upon EC is nothing but sigma L upon EL. Modifying this expression, I can write this expression as the ratio of sigma f to sigma m. That is, what is the stress produced in the fiber and what is the stress produced in the matrix. That is the ratio between the stress in the fiber to the stress in the matrix, and it can be written as EF upon EM. We have said that the strain in fiber and the matrix is the same, but the stress is not the same. So stress, we say sigma F upon sigma M is equal to EF upon EM. That is the ratio of the stiffness of the fiber to that of the matrix. So we simply can say that the stress in the fibers is sigma F by sigma M times higher than sigma M. So fibers in a composite material are stressed much higher than the matrix material in the composite material. And how much higher? EF upon EM times higher than the matrix material. Okay. So we were interested to find out, that was regarding the stress. So I write the same expression here, and we are interested to find out the load sharing between the fibers and the matrix, that how much of the load is shared by the fiber and how much of load is shared by the matrix. As a designer of a composite material, it may be desirable for us to have a very high load sharing by the fibers, because they are the stiffer and the strong components in the matrix. So when I take along this this expression here, we can also write this expression here as sigma f upon sigma L. Sigma f upon sigma L is nothing but EF upon EL, and sigma f upon sigma M is nothing but EF upon EM. So we are getting these two expressions from the first expression which we derived in the last slide. Okay. So moving forward, if I want to find out the ratio between the load taken by the fiber, that is PF, to the load taken by the matrix, that is PM. So PF upon PM we can simply write it as PF can be written as sigma F, that is stress in the fiber, into area of the fiber upon stress in the matrix into area of the matrix. This is a simple expression. We are simply writing the load in the fiber and the load taken by the matrix here. And now we already have with us that this sigma F upon sigma M can be written as EF upon EM. So when I use this expression in the yellow box here and I put it here, I can write this expression as EF AF upon EM AM. And what I do further, I multiply it by AC upon AC just to get an idea about what we refer to as volume fractions. So when I do that, I can simply write this expression for PF upon PC. The load taken by the fiber to the load taken by the matrix is nothing but EF into VF upon EM into VM. So EF by EM is what we already have been talking about, the ratio to the stiffness, and VF upon VM is nothing but the ratio of the volume fraction of the fiber to volume fraction of the matrix. Okay. Next, I may be interested to find out what is the ratio of PF to PC, that is the load taken by the fiber to the total load taken by the composite material. That's what we have applied onto it. So we applied load PC onto the composite material, and we have said that that load is shared between the fiber load, that is PF, and some of it is taken by the matrix also, that we say is PM. So what is the ratio of the load taken by the fiber to the total load applied on the composite? I can simply write this expression as sigma F into AF, that is PF, and PC is what we have, that is PF plus PM. So PF is sigma F into AF plus sigma M into AM. Going forward, what we do, we then divide this expression, whole of the expression, by sigma M. So when I divide this expression by sigma M, what I get is sigma F by sigma M into AF upon sigma F by sigma M into AF plus AM. And then what I know, that this sigma F by sigma M is what? Here, sigma F by sigma M is EF by AM. So EF by EM is substituted here, and similarly here. And then I get this expression. As EF upon EM upon EF upon EM plus AM by AF. So we are writing an expression for the ratio of the load taken by the fiber to the load taken by the matrix material. So EF upon EM, and it is equal to EF by EM upon EF by EM plus AM by AF. Taking this expression forward here, so the same expression I am writing it here, and then what we do, we then write this A's in terms of volume fraction. So we write that EF by EM and replace this AM by AF by the VM by VF term, which gives me the ratio. It gives me the ratio PF by PC, the ratio of the load taken by the fibers to the total load of the composite. So what is basically, it is nothing but the share of the load taken by the fiber out of the total load acting on the composite. It can be written as the ratio of EF by EM upon EF by EM into plus 1 upon VF minus 1. So what we observe here? So what we observe here is that the ratio of PF to PC, that is what is the contribution of the load sharing of the fibrous material or the fiber to the total load applied. It depends upon, again, two parameters: the ratio of EF to EM, which we have said earlier also in our last example also, that it is an important parameter, that stiffness ratio of the fiber to the matrix, and then the second one is the VF, that is the volume fraction. Okay, so what we see next is that when I plot this exercise, when I plot this expression here, so when I plot this expression here, the expression which we said, this expression, it is PF by PC is this expression. It depends upon EF by EM and then other parameters. So when I plot PF upon PC, when I do that, and I have plotted this in simple Excel, In simple Excel, I'll provide you an assignment which will make for using a simple spreadsheet to plot this graph. So what we observe here? We understand that we are plotting the ratio of PF upon PC. Obviously, it varies from around 0 to 1. And here on the x-axis, we have the volume fraction, the fiber volume fractions. And what we are seeing here, I have plotted it for various values of the ratio EF upon EM. So EF upon EM is 1, which simply means that the fiber and the matrix are the same material. EF by EM equal to 10 means fiber is 10 times stiffer than matrix. And similarly, we see others also, that EM by EF is 30, 70, and I have plotted up to 100. So what we observe? We observe here that for as you keep on increasing the value of EF upon EM, the percentage of the load shared by the fiber, that is the ratio PF upon PC, is increasing, and even at a lower volume fraction of around, let us say, 0.2 also, we are able to observe that most of the load is taken by the fibers. That's what we say. So when EF by EM is high, even small volume fraction will also make fibers to take most of the load in a composite, and that is what we intend to do, that a composite material, and it will make the composite stiffer. So we say that even when you use a high stiffness ratio between EF by EM, that is fiber and matrix stiffness is high, the ratio between fiber and matrix stiffness is high, then even for smaller volume fractions, we find that most of the load is taken by the fibers themselves. Okay. Let's talk about the next topic here, which we say is the failure of the unidirectional composites. Okay, we have already seen that how we can predict the density of the unidirectional composites, how we can predict the modulus of the unidirectional composites along the L direction, and how we can predict the load sharing of the unidirectional composites again along the L direction, that is along the direction of the fibers. The next topic which we pick up here is how do these composites fail. We initially have discussed in our class that the matrix is very tough, but the stiffness is very low, whereas the fibers like glass fibers and carbon fibers, they are very stiff, but their toughness is low. So that is why we put them together to form a composite material, and then we see that the resulting composites may be exhibiting properties which is different from the fiber and the matrix itself. So let us see on a chart here. So what I'm plotting here is the sigma versus epsilon chart, that is tensile stress versus axial strain chart. And when I see the green one here, so this green one represents a brittle fiber. So we understand that the stiffness is high, the slope is quite high, and then the strain, the maximum strain at the failure is very low. The area, the epsilon max is somewhere here, it's very low. This is how a fiber behaves. And in this context, we define sigma Fu. What is that? The ultimate strength of the fiber. And epsilon Fu, that is the ultimate strain of the fiber, the strain at which the fiber will break. Then the red curve here now shows that it is a ductile matrix. So we have a brittle fiber represented by the green line, and a ductile matrix represented by the red line here. And in this curve now, curve for ductile matrix, we define sigma mu, which we say sigma mu is nothing but the ultimate strength of the matrix material. It may be a polymer material for our case to begin with. And then what is the purple line here? So the purple line here now refers to the resulting composite. So I have combined the brittle fibers and the ductile matrix with some volume fraction, and I expect that the resulting composite, the stress strain behavior may be something like this. And if you look at it carefully, I have put it in two parts. So the purple line almost is elastic, is a straight line with a linear elastic line, and then after that, after it crosses this epsilon fu, after it crosses this epsilon fu, we have put it in a dotted line. We'll see what is the meaning of this. So one thing is clear, that when you load the fibers separately, they behave with like this. When you load the matrix separately, they behave like this red line. What happens when you make a composite out of it and then load the composite material? We are interested about that how does it fail. So individually they are failing by the blue line and the red line, and their failure strength is given by sigma fu and sigma mu. And accordingly the failure strains are also given as epsilon fu and epsilon mu. I'm interested about that what happens here in this composite material, how does it fail, and how we are able to predict the failure strength of the composite material here. Okay, so we are seeing here that it will fail here. Look at it carefully, that the matrix alone could have withstood this much amount of strain here, too large a strain. The fibers which are there in a composite material, they cannot sustain this much amount of strain. So once you start loading the composite material here, it will follow this purple line, initially straight line here, but once the strain in the composite material goes beyond the epsilon fu, that is the maximum strain that can be withstood by the fibers here, the fibers will break. And what happens because of that, that's what we will see here. So we see here that in almost all the cases, sigma fu is much higher than sigma mu. That is, the fiber happens to be much stronger than the matrix material here. So I define now, so for a considerably high volume fraction. So I will go to later on that what is the meaning of this considerably high and why do I write considerably high volume fraction. What happens on loading of the composite material, most of the load is shared by the fibers. We have seen it already in our last previous slides, that what is the ratio between PF upon PC, that is the load shared by the fibers to the total load of the composite. And we have seen that when for high values of EF upon EM, even 15-20% volume fraction can actually make most of the load to be shared by the fiber. So we say most of the load is shared by the fibers here for a high volume fraction. If volume fraction falls below this, it may be very, very low, then something else may happen. But we'll go to that case later on. But right now we're saying it is considerably high, and that is why most of the load is taken by the fiber. So what happens on increasing the load? So when you keep on increasing the load, the tensile stress increases and the failure takes place. Failure of the composite takes place when the strain in the fibers reaches epsilon fu. So the failure of the fibers will take place. So the fibers will fail. So what will happen then? So in a composite material, you had fibers which were in the longitudinal direction and the matrix which are putting them together, which are binding them together. So when you go beyond this strain value, fibers break. So what happens to the load which was taken by these fibers? So that whole of that load immediately shifts to where? It will shift to the matrix material, which still from strain point of view, it can take strain. But so this load is shifted to the matrix, but because most of the load was taken by the fibers, which was very, very high load, the matrix will not be able to sustain it. And immediately the failure will occur. And the composite failure will occur immediately. That's what I'm saying. The composite failure will occur immediately after this, the moment. So this happens when you have a high volume fraction. There will be considerably high volume fraction. And let me keep it pending that what is the meaning of considerably high volume fraction here. Okay, there's another thing possible. So the second case which we can see is that obviously the first statement remains the same, that the fibers are much stronger than the matrix material, but when the volume fraction is low. So let's say the volume fraction is very low, 1%, 0.5%, 2%, very small amount of fibers are there. So when the amount of fibers is very, very small, and the amount of fibers is very, very small, obviously the load taken by the fiber is also less. So negligible load is shared by the fibers. Most of the load is taken by the matrix itself. So then what happens when you increase the load? When you increase the load and when you go beyond epsilon Fu, when you go beyond epsilon Fu, obviously the fibers will break. So when you go beyond epsilon Fu, the fibers will break. So whatever load the fibers were carrying, it will be shifted to the matrix. But because they were carrying a very small load, that is why the matrix material will be able to take, it may sustain that load. It may sustain that load, and the failure may not occur here for the composite. Immediate failure may not occur here. So for high volume fractions, the moment fibers break, you may see that the failure of the composite is immediate. For very small volume fractions, very small volume fractions, when this occurs, the fibers break, but because they were carrying very small load, and that is why matrix material may be able to take that load to some extent, and the failure of the composite may not happen immediately. Okay, let us look at it in a different way. So what I see here, the same discussion here, that I have the same stress strain diagram, and I have the fiber, the matrix, and the fiber here, the matrix here, and the resulting composite material here. And we are saying here that the total load on the composite is what? PF plus PM. So some of it is taken by the fiber and some of it is taken by the matrix. This we have already described previously, that how you can calculate the ratio, that what is the fraction of the load taken by the fibers and what is the fraction of the load taken by the matrix, which is the rest after, which is actually PC minus PF. And this is how we say that the slab model, which I have been referring to in our discussion, that and we'll continue with that slab model in this discussion also. So I have two cases here as previously discussed. Case A, we say, is a very small volume fraction when you put very small amount of fibers, and most of it is, let's say, very small means maybe 1%, just 1%, but we may be able to calculate that. And the second case is then sufficiently high volume fraction, and these are the two different conditions here for which the failure may be predicted and the failure will be different. So for case 1 you may get a different expression, and for case A, sorry, you may get a different expression, and for case B we may get a different expression. And let's see how we go for these expressions here for predicting the failure of a composite, which will actually lead us to predicting the strength of the composite along the longitudinal direction, that is sigma Cu, that is ultimate strength of the composite. So we already know what is the ultimate strength of the fiber, we already know what is the ultimate strength of the matrix, and we are interested to find out what is the ultimate strength of the resulting composite material, that is sigma Cu.